Hi everyone, this will be the fourth and final video lecture on Focus 3b, which is involving the entropy changes of entropy changes accompanying specific processes. In this particular video, we're going to be looking at composite processes. So what happens when two variables are changed at once, right? So this is going to be best demonstrated by an example. So I've taken this one directly from Atkins, and so this is going to be example 3b.1 on page 91. So, thus far, every entropy change we have considered has been for a single process. So how do we calculate the change in entropy of a process if two or more variables are changed during the course of that process? In many processes, more than one parameter changes, because entropy is a state function for an isolated system or for delta A, the change entropy total of a reversible process. The changes in entropy can be calculated as distinct steps and then added together. So this is best illustrated, like I said, in this example from Atkins. So the problem states it's asking to calculate the entropy when argon gas at 25 degrees Celsius and 1 bar of pressure in a container of 0.5 decimeters cubed, which is a liter. It's allowed to expand to 1 decimeter cubed and is simultaneously heated to 100 degrees Celsius. So we're changing both volume and temperature simultaneously. We're going to assume the molar heat capacity at constant volume is equal to that of a perfect monoatomic molecule. So which argon is a okay approximation, helium's better. So what I've done is organize that presentation of the problem into givens, finds, assumptions, and equations. So let's look at the solution. First, we're going to rationalize it, and then we'll go through with the actual numbers. So as this problem stands, the temperature, pressure, and volume are all changing throughout the process. From the setup of the problem, we can assume the amount of argon gas remains constant, so that at least means N is constant, but I'm still changing P, T, and V, right? The perfect gas law is an equation of state, so if the number of moles remains constant, then we only really need to know two of the three changing variables, because by definition of a state function, that last variable can be determined and is set by the other known variables. This allows us to concentrate on only two changing variables instead of three, so making our lives easier. So based on the setup of the problem, changes in volume and temperature are the variables we're focusing on. So to make our calculations and lives simpler, we're going to take advantage that delta S is a state function for isolated systems or for reversible processes, and we're going to break this down into two distinct steps. First, we're going to consider the isothermal expansion of gas from a volume of 0.5 liter to 1 liter, and this allows us to focus on the change in volume while ignoring the changes in temperature. And then what we're going to do is evaluate what happens when the temperature is increased from 25 to 100 degrees at this new, larger volume. Since we've been given P, T, and V of the initial state of the system, we can actually calculate the number of moles of argon gas, right? Because of the state function, if I know 3 of the 4 parameters are being constant, I can always solve for that last variable. So this number will remain constant throughout our calculations because of the constraints of the problem. So I've rearranged the ideal gas law to solve for N. I plugged in our initial values, and the number of moles of argon are now known at 0.0201 moles of argon gas. So, if we're going to evaluate the entropy change of the isothermal expansion of gas from V1 from V2, well, we can start with the definition of entropy. So it's ds equals dq rev over T. We know for reversible work, any changes in reversible work is going to be equal to negative P dV. And if we substitute in the ideal gas law into negative P dV, we get negative nRT over V dV. We are constrained, we actually chose the constraints. We said this is going to be an isothermal expansion, so we're not changing temperature. So it becomes the internal energy of an isothermal, the change in internal energy of an isothermal process will then be the Q rev plus W rev. It's going to equal to 0, because it's a definition of an isothermal transition is going to be a change, the du is always going to be equal to 0. So any heat lost by the system or any work done by the system is going to be replenished by the surroundings when the surroundings dumps more heat in, so that any heat lost will then be replenished, so the total is going to be equal to 0. So any internal energy spent as work is replenished as heat flowing into the surroundings, or any heat, in this case we're not losing any, but if heat did leave, would also have to be, it would be compensated for by flowing in from the surroundings into the system. So we rearrange this equation because we know Qrev plus Wrev equals 0. Now Qrev equals negative Wrev. I can substitute that back into the definition of entropy, so ds equals negative Wrev over T. I substitute in my definition of what reversible work is, negative P dV over T. Substitute in, that becomes positive P. Substitute in P from the ideal gas law. nRT over V dV over T is our new equation for determining the entropy change for this isothermal expansion. So lucky for us, if we look here, we have a variable and it's infinitesimal, so we can technically integrate. So if we look here, we can integrate from SI to S final. That's going to be our ds. And then we can also integrate from V initial to V final based on our variable and our infinitesimal. You pull out all the constants, which is n and r because the t's cancel. So nr, ln, vf over vi. All that work actually comes from a derivation that we've done in previous lectures. So all we need to do now is plug in our values. So there's our moles of argon. There's our ideal universal gas constants in units of liters mole per liter atmosphere per mole Kelvin. And then we take the natural log of that change in volume. So there's our 1 liter or 1 decimeter cubed over the initial volume, which was a half a liter or a half a decimeter cubed. Doing out the math, we find out that for step 1, that isothermal expansion, the entropy increases by 0.166 joules per Kelvin. Now that we've increased the volume, and we're taking advantage of delta S under these conditions being a state function, we can now evaluate what happens at this new larger volume, what happens to the change when I heat from T1 to T2. And again, I can start with our definition of entropy. At constant volume, we know dQ_rev is going to be equal to du, and at in the definition of heat capacity at constant volume, it can be substituted in for du. It's a rearrangement of the definition of heat capacity. Oh, sorry, I skipped a step. Sorry, dQ_rev we know equals CVm times dt, so we substituted in the definition of heat capacity. So now if we look here, our infinitesimals, we have, just an infinitesimal, dt, t, so variable with an infinitesimal, I can integrate. I'll integrate from SI to SF, will give me my delta S, and then on the right-hand side, I can take out my constant, which is my heat capacity at constant volume. It's taken outside the integrand. I can then integrate from Ti to Tf for 1 over T dt, and I'll get this equation here. If I can plug in my values, we assume that argon will behave as a perfect gas, so there's my CVm, which is 3/2 R, multiplied by the natural log of my T final, so there's my 100 degrees Celsius, converted to Kelvin, divided by my, I forget what the initial value was, 25 degrees Celsius at converted to Kelvin. Step 2 is then an increase in entropy of 0.0564 joules per Kelvin. And then if we add those two steps together, so our isothermal expansion added to isochoric heating, we end up with our final answer that for the, under these conditions, the delta S of the system increases by 0.173 joules per Kelvin.